Alright, grade 11 chemistry. This is a quick note on combustion reactions. It's a Thursday, so why not have an easy one before we head off for the weekend. So combustion reactions, here's what we're going to do. First we're going to balance some complete combustion reactions. Then we'll talk about conditions for incomplete combustion. We'll talk about carbon monoxide, which is one of the most dangerous products of incomplete combustion. Then we'll balance some incomplete combustion reactions. So not a lot to do today. All of these reactions are very, very similar. Let's get started with combustion. So combustion, basically fire needs oxygen. Oxygen is the most common oxidizer in a combustion reaction. It's 21% of the air. You can have fires in chlorine gas. You can have fires in fluorine gas. But this is, we're going to be specifically talking about oxygen fires when we talk about combustion reactions. So combustions have oxygen, and we even run on something that could theoretically be called a combustion reaction. This is called cellular respiration. We take the oxygen, combine it with glucose, and we get CO2, gaseous CO2, and liquid H2O. We breathe out the gaseous CO2, and the liquid H2O ends up either in our bodies or peed out or whatever it's going to do, and we need the oxygen as well. So we do the same thing. We do a straight up and down combustion reaction in our bodies, in multiple steps, mind you. We don't do it all in one shot, or else we'd be burning on the inside all the time. So balancing combustion reaction, balancing a complete combustion reaction is pretty straightforward. Your hydrogens become waters, your carbons become CO2s, and then we count up the oxygen and adjust the O2 as needed. So let's just choose a hydrocarbon to combine with oxygen. I don't know. Let's do C6H8. There's a hydrocarbon. We're combining it with oxygen. If it's a complete combustion, we have as much oxygen as we need. So we know we're going to make CO2. We know we're going to make H2O. We're going to make CO2 and H2O. How much CO2? Well, we have 6 carbons, so we're going to make, I'm going to change colors here. We're going to make 6 CO2 because there's 6 carbons. How much H2O? Well, we have 8 hydrogens, and there's 2 hydrogens for each of these, so we make 4 H2O. That's balancing our carbons and our hydrogens. Figure out how much oxygen. We just need to take stock of how much oxygen we've used. 6 O2s is 12 oxygen. 4 oxygens here is 4 oxygens. And so together right now, we've got 16 oxygens on this side. 16 oxygens. 12 from our carbon dioxide and 4 from our H2O. 16 oxygens. To balance that 16 oxygens, we have O2 over here. So we need 8, right? 8 O2s. So simple combustion reaction, it's really just figuring out how much oxygen you've got. That can sometimes be tricky. There's only kind of two ways that this can get more complicated. The first way that this can get more complicated is if we end up with an uneven number, if we have an odd number of oxygens. So to talk about that, let's say we have 7H14, and we'll burn that in oxygen. All right, C7H14, we'll burn that in oxygen. We know we're going to make CO2. We know we're going to make H2O. Let's work out our numbers. We have 7 carbons. 7 carbons, so we can make 7 CO2. We have 14 hydrogens. Each water takes 2 hydrogens, H2O. So we can make 7 waters as well. 7 CO2 and 7 H2O. Now we can figure out how much oxygen we have. These 7 CO2s is 14 oxygens. These 7 H2Os is 7 oxygens. When we add that up, 14 plus 7, we get 21 oxygens. 21 oxygens that we have. But we can only do this in packs of O2. So there are 2 ways to solve this problem. 2 ways to solve this problem. The first way is to do 21 over 2. We have 21 over 2 oxygens. right? Which is fine. Remember, there's trillions, quadrillions of these things in the reaction. So what we're saying here is we have instead of having 10 of them, we have 10.5 of them, 10.5 billion, right? Instead of 10 billion, we have 10.5 billion. So if you don't like fractions, you can write 10.5. That's okay, but fractions are better. So 10.2. That's one way to solve it. The other way is to multiply everything by 2. So if we come up to an odd number of oxygens, multiply everything by 2. Make 2 of these, make 14 of these, make 14 of these, and now instead of 21 oxygens, we need 42 oxygens because we multiplied everything by 2. And now we can safely say that we take 21 O2, so now it's balanced. So 2 ways to do it. That's the first way it can go a bit weird. The second way it can go a bit weird is if we add some oxygens on the left side. So let's say we're burning ethanol. That's alcohol, the stuff that's... ethanol is C2H5OH. That is ethanol. That's the formula for ethanol. Plus O2. You know, I'm going to move this over so that I have more room. Let me do that. C2H5OH is ethanol plus O2. And we're going to balance it. We're going to make CO2 and H2O. It's like, okay, I've got an oxygen here. I've got an oxygen. What do? Well, we use the same techniques. We use the same tricks. The carbon tells us how much carbon dioxide we can make. We have 2 carbons. We can make 2 CO2. The hydrogen tells us how much water we can make. We have 5 here and 1 here. We have 6 hydrogens. We can make 3 H2O. And then we can continue with the same trick. 2 CO2s is 4 oxygens. 3 waters is 3 oxygens. 4 oxygens, 3 oxygens together. That is 7 oxygens. 7 oxygens. Right. I always hate that oxygen is an O because it looks like 70. Right, we have 7 oxygen there. We have 7 oxygen there. One of our oxygens is in our starting material, so there's 1 oxygen here. Right, and here's our balance. 1 here, 7 here, which means we need 6 oxygen here in our O2, which means if we put a 3 here, we'll be balanced. Right, so that'll all balance out. We have 7 oxygens on this side and 7 oxygens on that side, and that's how we balance the combustion reaction that involves oxygen. Still the same tricks. Carbon makes your CO2, hydrogen makes your water. Count up your oxygens and balance them out. So that's balancing complete combustion reactions. That's our first. Part of the lesson. Now we're going to balance incomplete combustion. Incomplete combustion. Balancing incomplete combustion. Oh, actually, it's conditions for incomplete combustion. Conditions of incomplete combustion. So, next up, conditions of incomplete combustion. Fire needs oxygen. And with enough oxygen, you can burn almost anything. These 2 great videos here. This one is this one's a chamber where they have reduced the amount of oxygen in the chamber to 15%, and they try to burn stuff, and it doesn't burn because there's not enough oxygen. Not enough oxygen. And there's this dramatic, he's got a torch and it just goes out. It's really quite wonderful. Right, outside 21% oxygen. Inside 15% oxygen, not enough to burn. And then the second video that's really great here is this one, which is doing a combustion using liquid oxygen. So that's liquid oxygen. If you do something with liquid oxygen, there's a lot of oxygen in the atmosphere around it. So here's in normal oxygen, it doesn't really burn. In 21% oxygen, doesn't really burn. But with the liquid oxygen, you get a heck of a reaction. Right? So oxygen's great. When we have lots of oxygen, we make a very exothermic reaction. But in an incomplete combustion, we don't have enough oxygen. You still make water, but there's alternatives for making the carbon dioxide. You can still release energy just making the water. So if you have the right conditions, you'll still have combustion happen, but it won't create CO2. So when there's not enough oxygen around, you get carbon monoxide and soot coming out. Carbon monoxide and soot, because there's less oxygen required to form them, right? CO2, 2 oxygens for every carbon. Carbon monoxide, just 1 oxygen for every carbon. Soot doesn't even have any oxygens at all. So that's what we call an incomplete combustion. In an incomplete combustion, there's not enough oxygen. And in fact, you can actually burn the soot and the carbon monoxide afterwards as well. So, complete versus incomplete. Here's complete combustion. It's white. The white is not smoke, it's just steam. It's actually just water vapor coming off of these cars and condensing in the atmosphere. Is why you see it more often in the winter than you see it in the summer. It's just like seeing your breath. Meanwhile, when you see this black smoke that comes off of especially diesel trucks and buses, that's because there's not enough oxygen coming in during that time while they're burning, and you end up with the soot, the black carbon soot. That's also, the stuff that's left behind when you, say, burn a match. You've got the soot on the end of the match. That comes from incomplete combustion. Because if it's complete combustion, it would be CO2, which is invisible and a gas, and H2O, which is clear. But this tells me that near the end there wasn't enough oxygen to burn that part of the match. So that's incomplete combustion. Soot is not particularly dangerous, but carbon monoxide is. So let's talk about carbon monoxide. Carbon monoxide, the other product, is very, very dangerous because it's colorless, it's poisonous, and it's heavier than the air, so it sinks. And you can't detect it. It's colorless and odorless. And what it does is it displaces the oxygen in red blood cells, like a single displacement reaction where it comes in and kicks it out, and then it stays there because it's got the highest affinity, it's got the highest activity for our red blood cells. So CO2 can't kick it out, and O2 can't kick it out. You might have a detector for it in your house. I know I have one in my basement. It's in my basement because it's heavier than air. Also, it's in my basement because that's where my furnace is, and my furnace is a gas furnace. So if something screws up with the air supply there, if it doesn't get enough oxygen, it might start making carbon monoxide. Hasn't happened yet. Hopefully it never will, but it's something to watch out for. So here you see a picture of what it does to your cells, right? The carbon monoxide just blocks oxygen from getting to your red blood cells, and then it stops it from circulating through your blood, and then your organs don't get enough oxygen, your brain doesn't get enough oxygen, you start losing oxygen. And because your brain needs oxygen to live and to think, your brain starts slowing down. You get headaches, you get drowsiness, shortness of breath, blurring of vision, right? Confusion, things like that. There's really interesting stories of people with carbon monoxide poisoning getting really paranoid and thinking that there's people in their house and stuff like that, and it turns out it's just carbon monoxide, and they've just been oxygen deprived, so their brain's going a little bit crazy because it hasn't had enough oxygen. So yeah, especially headaches. Headaches are a common, very, very common symptom. Yeah. That's carbon monoxide. A lot of people inadvertently poison themselves when they do something like grilling inside. They bring their barbecue inside, or maybe the power is out and the stove's not working. They'll try to cook stuff with a fire, but it's inside, so there's not enough oxygen. Because outside there's lots of oxygen coming through. Inside you've just got the room, and the carbon monoxide will creep up on them, because once again it's odorless and it's colorless, and yeah, not great. Alright, last piece here is balancing these incomplete combustions. Now the thing about balancing incomplete combustions is you have to know how much oxygen is available. Because if you don't know how much oxygen is available, then there's no way to figure it out. So I'm going to write up some combustion reactions and do not give enough oxygen to do a complete combustion. So let's try a few out here. All right, I'll try a few out. So let's burn, say, C3H6 plus. Now it's going to be O2. I need at least 3 oxygens to make 3 waters. I don't want too much oxygen. So let's just say we have 6 oxygens. So 3O2. We have 3O2. Right, we have 6 oxygens to distribute. We have to make the water. We have to make the water. So we're going to make our 3 H2Os. Right, 3 H2Os. So that's 3 oxygens down. 3 oxygens. 3 oxygens from our 6. We have 3 left. We have 3 remaining. 3 remain. 3 oxygens for 3 carbons. Right, 3 carbons from our C3H6, and we have 3 oxygens to distribute between our 3 carbons. So 3 carbons, 3 oxygens. How do I distribute it? Well, there's a couple of options actually here. You could do a carbon dioxide, 1 carbon dioxide, 1 carbon monoxide, and 1 carbon, just straight up. 1 carbon dioxide, 1 carbon monoxide, 1 carbon. That's possible. Or you could do 3 carbon monoxides. You could do that too. So 2 options here. Right. Both are fine. The real answer is somewhere in the middle, probably. You'll get a little bit of carbon dioxide, a little bit of carbon dioxide, and probably a whole lot of soot from this one. So that's one. Let's try a different one, just to get a hang of it. Again, every time there's an incomplete combustion, you have to know exactly how much oxygen you have. So let's try, I don't know, C10H16 plus O2. We're going to make H2O. We're going to need at least 8 oxygens. Let's go nuts. Let's say there's 7 O2 here. All right, let's say there's 7 O2s. How much water can we make? Well, we have 16 H's, so we're going to make 8 H2O. So out of our initial 14 oxygens, actually, let's kick up that oxygen number a little bit more. Let's say we have 10 oxygens. Let's say we have 10 oxygens. 10 oxygens. That means we have 20 oxygen molecules. Right, 20 oxygen molecules. 8 of them are used by the H2O. 8 of them are used here. So that means that we have 10 carbons and 12 oxygens. Right, we have 10 carbons and 12 oxygens to distribute now. So whatever combination of carbon, carbon dioxide, and carbon monoxide can get us 12 oxygens onto 10 carbons is an accurate way to balance this reaction, to make an incomplete reaction. So what are some options that we have? We could do, let's just use all the oxygen on CO2. Let's make 6 CO2. Right, that's all the oxygen gone. We still have 4 carbons, so 4 carbon. We can do that. 6 CO2 and 4 carbon. That works. If we had 5 CO2s, right? If we had 5 CO2s, we have 2 carbons left over. We're using 10 right now. We can make 2 carbon monoxides. 2 carbon monoxides. That's 7 carbons. 7 carbons. So we'd have 3 left over for just soot. Right? We could go 4 CO2s using 8 of our oxygens. Using 8 of our oxygens, because there's 4 O2s and there's 8 of those. Leaving 4 behind for 4 carbon monoxides. And now we're using 8 carbons here. We'll have 2 soot. That's another option. So yeah, as long as you can manage the amount of carbon and the amount of oxygen that you're making, you will have an appropriately balanced incomplete combustion reaction. And it's really just figuring out how many oxygens you have left over in order to figure out which of these you're going to make. Yeah. But you always have to make the water, right? Keep in mind today, we always have to make the H2O, but the carbon can take different forms. It can take CO2, CO, or C. The more CO2 you make, the more energy you release from your combustions. So we want complete combustion for maximum energy. And also because it doesn't create any carbon monoxide and it's not poisonous and stuff like that. And it doesn't make soot, which, is not great because it gets everywhere and it's black and it gets on surfaces and it can screw stuff up. Yeah. And that's it. That's the whole presentation. Yeah, have a look in the description for those 2 videos, and I will see you guys in class. That was a quick one.